Okay, YouTube, this is my second video on function transformations in which we're going to focus on stretches and shrinks of functions. So I say in our previous section of chapter 1 we learned that multiplying all the y values or f of x values by a constant can vertically stretch or shrink the graph of a function either away from or towards the x-axis respectively. And I have Desmos open here. I basically just kind of want to go to show this, but if we were to have some function f of x maybe equals x. This is our linear parent function here. I'm even going to drop in a table of values where we can see some inputs and outputs. The real question becomes is what happens when I take a constant, I'll say like a, we'll call it a, and I take it times f of x, and we'll let a be a number here, and I'm going to say a is 1. If I take all these y values from my function, and I say take them times 1, well then I get some new function where I would have the same values as the original values here. You can see that 1 times f of x gives us all the same outputs for the initial inputs. But what if I were to take now all of my y values on this original function and double them? That is, take 2 times all of my y values, or 2 times all the function values. You could see that what's happening here is all the initial y values here stretch twice as far away from the x-axis, okay? So if it was initially at a height of 1, now it's at a height of 2. If it's initially at a height of 2, now it's at a height of 4. What if it's at a height of 0? Well, 0 times 2 is still the same thing as 0, but you can see that the bigger this number gets that I take times my y values here, you can see how it's affecting the initial y values there. They are just simply growing and stretching further and further and further away. Now, on that note, I do want to say something that's really important here. Taking everything times 1 keeps everything the same. Anything bigger than 1 is going to vertically, what we say, stretch our function. What would happen if we were to take now all the y values times, say, a half? Make this 0.5. And what you notice is, well, all the y values are now half of the original height of the initial y values, okay? So there is something to be said about this. If we were to take now all the y values times a number bigger than 1, it's going to vertically stretch it. If we take all the y values between a number between 0 and 1, it actually vertically shrinks it, okay? So what you're going to see on this note here is essentially this. I'm going to start with the vertical stretch and shrink before we talk about the horizontal stretch and shrink. But basically, the graph of y equals some number times all the initial y values of some parent function is a vertical stretch or shrink by a factor of a, we say. So for instance, when we took it times 2, we say vertical, stretch by a factor of 2. But it'll be a vertical stretch or shrink by a factor of a of the initial just plain old f of x function that we were given in the first place. So it's worth noting that we're only considering a values that are positive, and we say that a is not allowed to be 1, well, because if you take all the y values times 1, you would just have the initial function here. We say y equals f of x. So the note here basically that we want to make sure that we consider is this. Multiplying all the outputs by a will stretch the graph vertically away from the x-axis if and only if a is some number bigger than 1. So in other words, if a is greater than 1, we have vertical stretch. We have vertical stretch, okay? And if a, now this is important, is between 1 and 0, not including either of those, we have vertical shrink. Remember, we're only considering a to be positive. So these are the only possible values for a there, where we exclude allowing it to be 1 and 0, say, okay? So now let's consider what we mean by horizontal stretch and shrink. If vertical stretch and shrink is caused by taking all the initial y values, the f of x values times some constant, how might we consider we're going to cause horizontal stretch and shrink? And you might guess that we'll take all the x values here times some number a, where a is a constant that is positive and is not allowed to be 1, because if it's 1, you're going to get the same thing as just plain old f of 1 times x anyways, which is the same as the initial function. So it's worth noting here that we say that the graph of y equals f of a times x, where we're now multiplying the x values by a constant, is either a horizontal stretch or shrink by a factor of 1 over a. In other words, by the reciprocal a of the original graph f of x. So what you see here is essentially this. If we want horizontal stretch, okay, horizontal stretch, let's say a is equal to a half, and I have f of 1/2 times x. This is actually going to be horizontal stretch because consider that we're saying that it is by a factor of the reciprocal of a. So if a is equal to a half, we're going to have a factor of 2 over 1, which is going to double the x values and cause them to be twice as far away from not the x-axis but the y-axis. And you'll notice here that if a is greater than 1, that would actually cause it to shrink, because let's say we had something like this, f of 2 times x, and we say, well, then this would imply that a is equal to 2. Then our factor of stretch here, in terms of a horizontal sense, is of its reciprocal. So it's a factor of 1 over 2, since this was 2 over 1, and that's going to be a factor of a half. And we can certainly observe this here. If we were to go back now and take this a value and multiply all the x values by that a value there, okay, and I'm going to say, well, we're going to change this so that these show us the outputs for a times x in here. You can see that if a is a number between 0 and 1, I'll make this like a half here, a half. You can see that all of the initial x values have stretched out further from the y-axis. Okay, now it's, this x value is 4. This initial x value here to the left of it was 2. This x value here is 2. This one was 1. And also, if a is bigger than 1, we have this now horizontal shrink where it's starting to come back into the y-axis. So now what we're going to do is take a look at how we can write some functions using this knowledge of horizontal stretch and shrink, vertical stretch and shrink. So just like in the last video, we're given some function here, f of x, some parent function. In this case, this isn't a parent function, I guess, but some function that we're given initially. And it's f of x equals the absolute value of x minus 1 plus 2, so it's in the absolute value or v graph looking family. What we want to do is write some function g whose graph is a horizontal stretch of the graph of f by a factor of 5. So let's talk about this. Remember, when we talk about horizontal stretch, we're saying we're taking some number times the x values here. And again, if it's stretch, okay, stretch, then we're going to say that it's some number between 0 and 1 because it actually stretches by a factor of its reciprocal if we're talking about a horizontal stretch. So we would say that if it's by a factor of 5 here, then the reciprocal of 5 is actually 1 over 5. So what we want here in this case is a function g of x that's the same as the original function f of x, but we say is stretched by a factor of the reciprocal of 1/5, which is 5. So since we have this now, what we can do is we can actually just do a substitution where we say, well, let's take all the x's out. There we go. And what we're going to do is we're going to substitute in this input here. We have 1/5 x, the absolute value of that minus 1 plus 2. This would be some new function. It would be the same as the initial function if you graphed it, except for it would be stretched away from the y-axis, okay, by a factor of 5 and have horizontal stretch. Likewise, if we were to say, let's write a function h of x. Okay, so we have some function h of x. We say this graph is a vertical shrink of the graph of f by a factor of 0.25. Now let's recall something here. If we want to affect this graph vertically, then we should have some new function here where we're taking all the initial y values and we're actually multiplying them by this constant, or I should just say in this case, really quickly here, some number a. If you multiply the y values by a, it's going to stretch them vertically since we're multiplying the y values by a constant. Now keeping in mind that a, in terms of vertical stretch, is kind of just straight up. What I mean is it's not by a factor of its reciprocal, but by a factor of a itself. It is stretched by a factor of a, itself. So we say that if h of x is really just f of x, but we want it vertically shrunk by a factor of 0.25, we're going to say, well, let's take all the y values here and we'll multiply them by 0.25. And again, we'll just do a substitution. We say 0.25 of f of x. Well, the f of x, remember, is the absolute value of x minus 1 plus 2. And what we can do is we can actually distribute this. Now, I'm not meaning to put this arrow looking like it's going to go inside the absolute value. Remember that 0.25 times that absolute value, that 0.25 has to stay on the outside. But we say 0.25 times 2 here is actually a half. So we would get a half. This new function here would now be vertically shrunk by a factor of 0.25 or 25% of its original size, or a fourth. So what we're going to do on this last part here is essentially look at these and use a graphing calculator to check our answers with. So it says write a function g whose graph represents the indicated transformation of f, and use a graphing calculator to check our answers. So in each instance we have some different function f, but in this first one here we say f of x is some 2x minus 1, so some linear family member here. We want to horizontally stretch this by a factor of 3. So again, let's recall this. If we wanted to affect a graph with horizontal stretch, we're going to multiply all of the x values by some a. And since it's horizontal stretch, we're going to multiply by the reciprocal of a. It's kind of how that works. So here's what we're going to do. Since we want a factor of 3, we're going to say that a is the reciprocal of 3. It's 1/3. So our new function here, we say g of x. I think we want a function here. Yes, we want g. G of x is really just our f of x. And since we want horizontal stretch by a factor of 3, we say f of 1/3 times all the x values. And we do need to work a substitution here. So our substitution says, well, if your initial function is 2 times the input minus 1, your input now would be 1/3 x. We have 1/3 x. And I'm going to go ahead and multiply this here. 2 times 1/3 is just 2/3. We have 2/3 x. We still have minus 1. So using our graphing calculator, let's take a look at these two functions here. We had our initial function is 2. Oh, let me turn this on here. On. We have 2x minus 1. This is our initial linear function. Okay, we can see this here, 2x minus 1. What we wanted to do was horizontally stretch it by a factor of 3. Well, going back in here, we'd say, okay, well now I want 2/3. I'm going to put the 2 divided by 3 in parentheses. 2 divided by 3 x minus 1. That was our new function that we were able to get here as a transformation. And when I hit graph, we'll see this here. Our initial function is now everything is stretched away from the y-axis 3 times as far as it initially was with respect to x there. Okay, so let's take a look at one vertical shrink before we wrap this up. We say some function f of x is in the absolute value family, shifted up 1. We say let's vertically shrink this by a factor of 1/3. Now vertical shrink does not shrink by a factor of 1 over a, the reciprocal of a. It shrinks by a factor of just straight up a. So what we're saying here is this. If we have a function f of x and we want to vertically shrink it, we're going to say take all of the initial y values f of x and take it times some number a here. And in this case, we want to shrink it by a factor of 1/3. So we say that our g of x, our new transformed function, would be the same thing as our initial function where we're taking all the initial y values and cutting them by 1/3. So again, a substitution works here. We say 1/3 our function of x. And our function of x is the absolute value of x plus 1. Whoops. Yeah, I want to get rid of that there. So we say absolute value of x plus 1. I am going to distribute the third. So we get this new function here. We have 1/3 times the absolute value of x plus 1/3 times 1 is 1/3. So graphing these, let's go ahead and do this here. We say clear these out. Our initial function, we're going to have to go into our catalog here and pull out absolute value. But we have absolute value of x and quantity plus 1. So here's our initial absolute value graph that's been shifted up 1. We say what we want to do is vertically shrink this down to the y or the x-axis again. So now we have in parentheses 1 divided by 3 times the absolute value of x. Whoops, let's quit out of this. We need to go back to y equals 1/3. I think I know what I did here. Okay, so now into my catalog, I forgot to hit enter. So absolute value of x, and then we have plus 1/3, plus, in parentheses, 1 divided by 3. And since I erased my initial function there, I'm going to go ahead and put that back in. I apologize. We have absolute value of x. We had plus 1 there. So these will graph out of order, but we will see that this is our vertically shrunken function. Here was our initial function there. So every one of these y values on the initial function is being taken times 1/3, so they will shrink down.